In this video, we're going to do an example in which we're going to learn how to find the interval of convergence for a power series. In this example, we're given a power series with a general term -1 to the power n, x to the power n over cube root of n, and then n goes from 1 to infinity. We know it's a power series because the general term contains variable x. And as we discussed in the introduction video, for some values of x, this series may be convergent, and for some values of x, this series may be divergent. Our goal to find for what values of x the series is convergent, and we're going to present our answer in the form of an interval. In general, to determine the interval of convergence, we use the ratio test. So in other words, we apply the ratio test to the given series. In some cases, we may use the root test. Remember that according to the ratio test, a series converges absolutely if the following limit of the absolute value of a sub n plus 1 over a sub n equals to a number that's less than 1. So series converges in this case according to the ratio test. Well, let's try to set up this limit for our series. So it's going to be limit as n approaches infinity, absolute value, and here I have the ratio. In the numerator, I'll have to put n plus 1 term of the series, so it means that I'm going to take this general term and every n I'm going to replace with n plus 1. So that's -1 to the power n plus 1 times x to the power n plus 1 over cube root of n plus 1. In the denominator, we'll just have this general term a sub n. So I'll just copy it down. Next, we need to simplify this complex fraction. As we apply the absolute value, that becomes positive 1 no matter what power is, and factor of 1 can be dropped. So that means that we'll have limit as n approaches infinity, absolute value. Okay, so I'm going to rewrite the numerator, x to the power n plus 1 over cube root of n plus 1, and I dropped -1 that became positive 1. And then I'm multiplying that by the reciprocal of the denominator, which means that cube root of n is going to be in the numerator. And then, okay, -1 to the power n goes away, and then x to the power n is in the denominator. Next, let's simplify this a little bit. So what I can do, I can rewrite x to the power n plus 1 as x to the power n times x to the power 1. Let's see. X to the power n times x to the power 1, which is just x, cube root of n over cube root of n plus 1 times x to the power n. And now I can see that x to the power n goes away. I can divide out that, and that's what I'm left with. X cube root of n over cube root of n plus 1. Now, how do we find the limit of this expression? Well, there are two variables, n and x. But keep in mind that we're finding limit here with respect to n only, so it only n approaches infinity. And that means that x can be treated as the constant in this case. So if I ignore x and I only look at expression involving n, what can I say about its limit? Well, I can see that the degree of the numerator is the same as the degree of the denominator, right? So the highest power on the top is exactly the same as the highest power on the bottom. So when that happens, then the limit is simply the ratio of the leading coefficients of the numbers that stand in the front. Well, since we treat x as the constant, it means that a limit, this limit as n approaches infinity, equals to x in the numerator and then 1 in the denominator, so it's just simply absolute value of x. So one more time, as you find limit here, treat x as the constant. Only focus on the expressions that involve n and then find limit same way as you always did. What is this result? Well, let's go back and remind ourselves what we're doing here. We're applying the ratio test. We said that this series is going to be convergent if, according to the ratio test, the result of this limit is less than 1. Now, what is the result? And we set up that limit, right? Here it is. We set it up, we simplified and found the limit. And now we can say that this series is convergent when the result is less than 1. So what is our result? Right here, absolute value of x. So that has to be less than 1 for series to be convergent. Now, to clarify this even more, well, let's think what it means that absolute value of x is less than 1. That is same as x in between the values -1 and 1. So what we're saying right now is that for all values of x that between -1 and 1, this series is going to be convergent. Does this mean that we found an interval of convergence? Well, that looks like an interval, right? Is that our final answer? Well, not yet. And the reason for that is the following. We also need to determine whether that series is going to be convergent at the endpoints. Notice how endpoints are not included right now. So less, strictly less, means that neither -1 or 1 are included. And the question is, do we need to include those endpoints? So after you conduct the ratio test in this matter, or root test in some cases, you have to perform steps on checking the endpoints, on whether series is convergent or divergent at the endpoints. And that's because the ratio test will always fail at the endpoints. Why couldn't I just write less than or equal to 1? Then endpoints would be included. But remember, what happens when a result equals to 1 according to the ratio test? Well, according to the ratio test, when result equals 1, then the test is inconclusive. That means that ratio test will only give us the open interval, and we'll have to do additional steps on checking the endpoints. And we literally do one at a time. So first we're going to say, let x be equal -1. So we're going to see what happens when x equals -1. What we do, we take -1 and we plug that value into our series. So it's no longer going to be a power series. We'll let x be equal -1. See what happens. So then I will obtain the series that looks like this and goes from 1 to infinity. I'm copying everything down except that I am replacing x with -1. Okay, so next here in the series I have x to the power n. I'm going to be writing -1 to the power n. So that's where I place that -1. And in the denominator, I have cube root of n. Well, that expression I should be able to simplify, right? How do I simplify it? Well, if I have two bases with the same power, I can combine them together under one power. So in other words, I can combine this base, -1, and the other one, which is also -1, under the same power. But what is -1 times -1? It's just 1, +1. And what is 1 raised to the power n? It's just 1, right? So in other words, the numerator simplifies to simply 1. 1 over cube root of n. And that's the series we obtain. And now we have to find a test to determine whether the series is divergent or convergent. And for that, we need to use the knowledge of different tests and ability to recognize some special series. So which one is that? So it's 1 over cube root of n, which is same as n to the power 1/3. So it's 1 over n to the power 1/3. And that is the p series, right? 1 over n to the power 1/3. So that's p series with power being equal 1/3, which is less than or equal to 1. And according to the p series test, it means that the series diverges. diverges. So at x equals -1, the original series diverges. Well, that will mean that we will not include -1. It will still stay as less than sign. Next, let's see what happens when we let x be equal 1. So let's test the other endpoint. Let x be equal 1. So same thing, I'm going to be plugging in 1 for x in this series. So that's going to be, n goes from 1 to infinity, -1 to the power n times 1 to the power n. That's where I plugged it in for x, over cube root of n. Let's simplify this general term. I know that 1 raised to any power is still 1. So overall, this is just 1. Anything multiplied by 1 is itself. So basically, this factor disappears, right? And that's how the series is going to look like. -1 to the power n over cube root of n. And now we have to determine if this series converges or diverges. Well, what kind of series is that? Well, because we have -1 to the power n in the numerator, it means that this is alternating series. And we're going to apply alternating series test. Remember, it has two conditions. Remember, the first condition is to ignore negative signs and basically take the absolute values of all the terms of the series and show if they are decreasing. If I call absolute value of all those terms b sub n, that's where I ignore negative sign, then I have to show that b sub n plus 1 is less than or equal to b sub n for all n. Well, let's look at that inequality. So b sub n plus 1, that's 1 over cube root of n plus 1, and then b sub n is 1 over cube root of n. Can we put less than or equal sign here? Yes, so obviously this denominator is larger than the one on the right, so that means that this fraction is always smaller or less than or equal to than the one on the right. So yeah, that condition is satisfied. And the second condition is to show that the limit of this absolute value term as n approaches infinity equals 0, right? So limit as n approaches infinity of 1 over cube root of n is 0, right? As n is getting infinitely large, this fraction approaches 0, so limit equals 0. The second condition is also satisfied. So we're going to say that the series converges by the alternating series test. Okay, so what does that mean? That means that at x equals 1, the original series converges. And that means that when we talk about the interval of convergence, we will be including this endpoint. So the interval of convergence, I'm going to put it here, is x between -1, not including -1, and 1 including 1. So less sign here and less than or equal to sign here. I can also use interval notation and write like that, from -1 to 1 with the bracket, right? So it's another notation. And as an additional exercise, it also would be good to note what's the center of this interval of convergence and what's the radius. And we can find it kind of from different places here. So one is just basically like straightforward way when we consider this interval from -1 to 1, parenthesis here and bracket here. What number is at the center of this interval? Well, it's 0, right? 0 is right in the middle. And what is the radius? Radius is this distance. That's 1. Radius equals 1, right? But we don't even have to look at the number line and look at the interval. What we can do, we can look at the result of the ratio test. Absolute value of x is less than 1. So it will give us the radius and center as well. So this number is always going to be a radius 1, and the number that stands next to x inside the absolute value, that's going to be the center. Well, obviously there is no number because center is 0, but the way we think about this expression is x minus a. So that explains why a, the center, is 0 in this case. But yeah, that's the answer, interval of convergence. Let me briefly recap the steps. So once you're given a power series and you're trying to find the interval of convergence, you start by applying the ratio test most of the time. In some cases, it could be a root test. Once you obtain the result of the limit, then you say that, well, that result has to be less than 0 because that's when the series is convergent. But you need to remember that the ratio test or root test, they fail at the endpoints of the interval. So this test is not going to tell us if that series is convergent at the endpoints, convergent or divergent. Because of that, we have to test the endpoints. So you plug in each value into the series one at a time, and you test the resulting series using one of the known tests. And then you determine if endpoints have to be included, both of them or only one of them or none of them. And that's how you determine the interval of convergence.